Hydration energy is one of the most important properties of ionic compounds because it explains how strongly ions interact with water molecules. Whenever an ionic compound dissolves in water, its positive and negative ions become surrounded by water molecules in a process known as hydration. During this process, energy is released because attractive forces are formed between the ions and the polar water molecules. This released energy is called hydration energy, also known as hydration enthalpy. In simple terms, hydration energy is the amount of energy released when 1 mole of gaseous ions becomes surrounded by water molecules to form hydrated ions in an aqueous solution. Water is a polar molecule with a partially negative oxygen atom and partially positive hydrogen atoms. Because of this polarity, water molecules are naturally attracted to charged ions. Around a positive ion, such as Li or Na, the oxygen end of each water molecule points toward the positively charged ion. Around a negative ion, the hydrogen ends point toward the negatively charged ion. As these water molecules surround the ion, they form a stable hydration shell, and the formation of these attractive ion-dipole interactions releases energy. The amount of hydration energy released depends mainly on the size and charge density of the ion. Among the S-block elements, ionic charge remains the same within each group. So the most important factor is ionic radius. Smaller ions have a much higher charge density because the same positive charge is concentrated into a much smaller volume. As a result, they attract water molecules much more strongly than larger ions. Stronger attraction produces stronger ion-dipole interactions, and stronger interactions release more energy during hydration. Therefore, smaller ions always have higher hydration energy than larger ions carrying the same charge. The infographic clearly illustrates this concept using the alkali metal ions. Lithium ion, Li, is the smallest ion in group 1. Because of its very small ionic radius, it has the highest charge density and attracts water molecules extremely strongly. A large number of water molecules surround the lithium ion very closely, forming a compact hydration shell. These strong attractions release a large amount of energy, giving lithium the highest hydration energy among the alkali metals. As we move down group 1 from lithium to sodium, potassium, rubidium, and cesium, the ionic radius gradually increases because each successive ion contains an additional electron shell. Although every ion still carries a positive 1 charge, the charge is now spread over a much larger volume. Consequently, the charge density decreases, and the attraction between the ion and surrounding water molecules becomes weaker. Since weaker attractions release less energy, hydration energy decreases steadily down the group. Therefore, the hydration energy trend for group 1 is Li K, Rb, Cs. This means lithium ion has the highest hydration energy, while cesium ion has the lowest hydration energy among the alkali metal ions. In simple words, the smaller the ion, the higher the hydration energy, the larger the ion, the lower the hydration energy. The same principle also applies to group 2 ions. Beryllium ion, B, and magnesium ion, Mg, are relatively small and possess high charge density because they carry a positive 2 charge. Consequently, they attract water molecules very strongly and release large amounts of hydration energy. As we move down the group from magnesium to calcium, strontium, and barium, ionic size increases, charge density decreases, and hydration energy gradually becomes smaller. Thus, hydration energy decreases down group 2 as well. The infographic summarizes this relationship in a simple sequence. A smaller ionic radius produces higher charge density. Higher charge density leads to stronger attraction between the ion and water molecules. Stronger attraction results in more energy being released during hydration. Therefore, smaller ions always possess higher hydration energy than larger ions with the same charge. Hydration energy has several important effects on the physical and chemical properties of S-block elements. It plays a major role in determining the solubility of ionic compounds in water. When hydration energy is sufficiently large, it helps overcome the lattice energy holding the crystal together, allowing the compound to dissolve more easily. Hydration energy also influences the stability of hydrated ions, the conductivity of electrolyte solutions, the heats of solution, and many biological processes involving metal ions in living organisms. One of the most interesting consequences of hydration energy is seen in lithium. Although lithium belongs to the alkali metals, many of its properties differ from those of sodium, potassium, and the heavier alkali metals. This unusual behavior is largely due to the exceptionally high hydration energy of the very small Li ion. Because lithium ions are so strongly hydrated, many lithium compounds show properties that resemble those of magnesium compounds, a phenomenon known as the diagonal relationship in the periodic table. It is also important to distinguish hydration energy from lattice energy. Lattice energy is the energy released when gaseous ions combine to form a solid ionic crystal, whereas hydration energy is the energy released when gaseous ions become surrounded by water molecules in solution. Both processes release energy because they involve the formation of attractive electrostatic interactions, but one occurs during crystal formation and the other during dissolution in water. Hydration energy is the energy released when gaseous ions become surrounded by water molecules during the hydration process. The magnitude of hydration energy depends mainly on ionic size and charge density. Smaller ions possess higher charge density, attract water molecules more strongly, and therefore release more energy during hydration. As ionic radius increases down groups 1 and 2, charge density decreases, the attraction to water molecules becomes weaker, and hydration energy decreases. This explains why Li has the highest hydration energy among the alkali metal ions, while Cs has the lowest. Hydration energy is an essential concept because it influences the solubility, stability, and chemical behavior of S-block compounds and helps explain many of the unique properties observed across the periodic table. The flame test is one of the simplest and most fascinating experiments in chemistry because it allows us to identify certain metal ions by observing the characteristic color they produce when heated in a flame. Every element has a unique electronic structure, and when its electrons absorb heat energy, they become excited to higher energy levels. These excited electrons are unstable and quickly return to their original lower energy levels. During this return, they release the excess energy in the form of light. Since the energy difference between electron levels is unique for every element, the wavelength and color of the emitted light are also unique. This is why different S-block elements produce different flame colors, and why the flame test is widely used as a simple qualitative method for identifying metal ions. The infographic illustrates the entire process of flame coloration. When a metal salt is placed in a flame, the heat from the flame provides energy to the electrons of the metal ion. These electrons absorb the energy and jump from their ground state to higher energy levels, a process known as electron excitation. However, excited electrons cannot remain in this unstable state for long. They soon return to lower energy levels, and while doing so, they emit the excess energy as photons of visible light. The color of this emitted light depends entirely on the energy difference between the two electron levels. Larger energy differences produce higher energy light, while smaller energy differences produce lower energy light. Because every element has a different arrangement of electron energy levels, each element emits a characteristic flame color. Among the alkali metals, lithium produces a beautiful crimson-red flame. This distinctive deep red color is one of the easiest to recognize during a flame test. Sodium produces an intense, bright yellow flame that is extremely luminous and often masks the colors of other elements if they are present together. This brilliant yellow color is due to sodium's strong emission around 589 nanometers. known as the sodium D lines. Potassium produces a pale lilac or violet flame. Since the potassium flame is relatively faint, it is sometimes observed through cobalt blue glass to filter out any yellow light from sodium contamination. The alkaline earth metals also produce characteristic flame colors. Calcium gives a brick red or orange-red flame, while strontium produces a brilliant crimson-red flame that is deeper and brighter than that of calcium. Barium produces a distinctive apple-green flame, making it easily distinguishable from the other Group II elements. These unique flame colors are widely used in analytical chemistry to identify unknown metal ions in laboratory samples. The infographic also highlights two important exceptions among the S-block elements. Beryllium and magnesium do not produce a distinct flame color under ordinary laboratory conditions. This is because their electrons require much higher excitation energy than the flame can normally provide. As a result, very few electrons become excited, and almost no visible light is emitted. Therefore, beryllium and magnesium are generally considered negative in the flame test. The sequence shown in the infographic summarizes the flame test process clearly. First, heat from the flame excites the electrons. Next, the electrons move to higher energy levels. Then, they return to lower energy levels. Finally, the excess energy is released as colored light, producing the characteristic flame color of that element. This simple sequence explains the origin of all flame colors observed during the experiment. The characteristic flame colors of the common S-block elements are easy to remember. Lithium produces a crimson-red flame, sodium produces a bright yellow flame, potassium gives a lilac flame, calcium produces a brick red flame. Strontium emits a crimson-red flame, and barium produces an apple-green flame. In contrast, beryllium and magnesium do not show any distinct flame color under normal laboratory conditions. The flame test has many practical applications in chemistry. It is commonly used for the rapid identification of metal ions in unknown compounds, especially in qualitative inorganic analysis. Flame colors are also used in the manufacture of fireworks, where different metal salts produce different colors. Strontium salts create brilliant red fireworks, barium salts produce green fireworks, sodium compounds give bright yellow flames, and potassium compounds contribute violet shades. Similar principles are used in signal flares, emergency lighting, and pyrotechnic displays. Although the flame test is a useful identification technique, it also has certain limitations. The test is mainly qualitative rather than quantitative, meaning it identifies the presence of an element but does not determine its exact concentration. In addition, sodium contamination is very common because sodium compounds are present in dust, glassware, and even human skin. Since sodium emits an extremely intense yellow flame, it can easily hide the flame colors of other elements. Therefore, clean platinum or nichrome wires are used, and cobalt blue glass is sometimes employed to filter out sodium's yellow emission when testing for potassium. It is important to understand that the flame color depends only on the electronic energy levels of the metal ion and not on the color of the compound itself. A white or colorless salt can still produce a brightly colored flame because the emitted light originates from electronic transitions within the metal ion after excitation by heat. The flame test is based on the excitation and de-excitation of electrons in metal ions. Heat from the flame excites the electrons to higher energy levels, and when these electrons return to lower energy levels, they emit excess energy as visible light. Since every element has a unique arrangement of electronic energy levels, each emits a characteristic flame color. Among the S-block elements, lithium gives a crimson-red flame, sodium produces a bright yellow flame, potassium shows a lilac flame, calcium emits a brick red flame, strontium produces a crimson-red flame, and barium gives an apple-green flame, while beryllium and magnesium do not produce distinct flame colors under ordinary laboratory conditions. the flame test remains one of the most valuable and visually striking techniques for identifying metal ions and understanding the electronic structure of atoms. The S-block elements occupy the first two groups of the periodic table and include the alkali metals of Group 1 and the alkaline earth metals of Group 2. Although each element has its own unique properties, all S-block elements follow predictable periodic trends as we move from the top of a group to the bottom. These trends occur because every successive element contains one additional electron shell, increasing the distance between the nucleus and the outermost electrons. This greater distance, together with the shielding effect produced by inner electron shells, weakens the attraction between the nucleus and the valence electrons. As a result, many physical and chemical properties change in a regular and predictable manner down the group. One of the most important trends shown in the infographic is the increase in atomic radius. Atomic radius is the distance from the nucleus to the outermost electron shell. As we move down Group 1 from lithium to sodium, potassium, rubidium, and cesium, or down Group 2 from beryllium to magnesium, calcium, strontium, and barium, each successive element gains an additional electron shell. Because of these extra shells, the outermost electrons are located farther from the nucleus, making the atom larger. Therefore, the atomic radius increases steadily down both groups. Larger atomic size is one of the main reasons behind many of the other periodic trends observed in S-block elements. As atomic radius increases, the attraction between the nucleus and the valence electrons becomes weaker. The increased distance and greater shielding by inner electrons reduce the effective nuclear attraction acting on the outermost electrons. Consequently, these electrons are held less tightly and can be removed more easily. This explains why ionization energy decreases down both Group 1 and Group 2. Ionization energy is the minimum amount of energy required to remove the outermost electron from an isolated gaseous atom. Since the valence electrons are farther from the nucleus in the heavier S-block elements, less energy is needed to remove them. Therefore, ionization energy decreases steadily from lithium to cesium in Group 1 and from beryllium to barium in Group 2. The decrease in ionization energy directly affects the chemical reactivity of S-block elements. Because the outermost electrons are removed more easily, the heavier elements lose electrons more readily during chemical reactions. Since alkali and alkaline earth metals react by losing electrons to form positive ions, easier electron loss means greater chemical reactivity. Therefore, reactivity increases down both groups. In Group 1, lithium is the least reactive alkali metal, while cesium is among the most reactive metals in the periodic table. Similarly, in Group 2, beryllium is the least reactive, whereas barium reacts much more vigorously with water, oxygen, and acids. Another important trend is the increase in metallic character. Metallic character refers to the tendency of an atom to lose electrons and form positive ions. Because the outermost electrons become easier to remove as ionization energy decreases, S-block elements exhibit stronger metallic behavior down the group. Thus, metallic character increases from lithium to cesium and from beryllium to barium. This is why the heavier S-block elements are stronger reducing agents and more readily form positive ions during chemical reactions. The infographic also shows the general trend in density. Density is the mass per unit volume of a substance. In most cases, density increases down the group because atomic mass increases much more rapidly than atomic volume. As heavier atoms are added, the overall mass of the metal increases significantly, causing density to rise. However, there are a few minor exceptions, especially among the lighter alkali metals, because atomic volume does not always increase uniformly. Therefore, the density of S-block elements generally increases as we move downward, although the trend is not perfectly regular. Melting point is another property that changes across the S-block. In general, melting points decrease down the groups, particularly in Group 1. Alkali metals possess only one valence electron, resulting in relatively weak metallic bonding. As atomic size increases down the group, the distance between positive metal ions and the sea of delocalized electrons also increases. This weakens the metallic bond, making it easier to separate the atoms. Consequently, less heat energy is required to melt the metal, and the melting point generally decreases. Although Group 2 shows some irregularities due to stronger metallic bonding involving two valence electrons, the overall tendency is still toward lower melting points as atomic size increases. All of these periodic trends are closely related and arise from the same underlying cause. As we move down a group, each atom gains an additional electron shell. The additional shells increase the atomic radius and enhance the shielding effect. The greater distance between the nucleus and the outermost electrons weakens the nuclear attraction, reducing ionization energy. Lower ionization energy makes electron loss easier, increasing metallic character and chemical reactivity. At the same time, larger atomic size weakens metallic bonding, leading to generally lower melting points. Thus, a single structural change, the addition of electron shells, explains the entire pattern of periodic trends observed in the S-block elements. These trends are extremely important because they help predict the behavior of elements without performing experiments. For example, since cesium has a larger atomic radius and lower ionization energy than lithium, we can confidently predict that cesium will react much more violently with water. Likewise, because barium has a larger atomic size and stronger metallic character than magnesium, it reacts more vigorously with oxygen and acids. Understanding these trends allows chemists to compare elements, explain their chemical behavior, and predict the properties of newly discovered substances. The periodic trends of S-block elements are governed primarily by the increase in electron shells down each group. As the number of electron shells increases, atomic radius increases, nuclear attraction weakens, and ionization energy decreases. Easier removal of valence electrons leads to greater metallic character and higher chemical reactivity. At the same time, metallic bonding becomes weaker, causing melting points to generally decrease, while density generally increases because atomic mass grows more rapidly than atomic volume. These predictable trends provide a clear understanding of why the heavier S-block elements are larger, more metallic, more reactive, and more chemically active than the lighter members of the same group.